In this section, we're going to be talking about pH. And again, pH is something that you have learned about. If you took physical science, you learned about pH all the way back there. Hopefully by now, it's pretty easy for you to recall that if something has a low pH, it's an acid. A pH of 7 is neutral. If you have a high pH between 7 and 14, you're going to have a basic solution. But now we're going to actually move into calculating what the pH of a solution is based on the number of hydronium or hydroxide ions that are in solution. There are 4 equations that you're going to need to be familiar with in order to work these problems. And just like I have done in all of your other modules, if you want to put these on an index card and use them on your test, I'm perfectly fine with that. Honestly, with these equations, I think that you're going to use them enough that you're going to have them memorized by the time you take the test anyway. So we'll talk about some basic definitions here. First of all, pH is the negative log of the concentration of the hydronium ions. And even though that concentration of hydronium ions is going to be in molarity, we don't put any kind of numbers on, or any kind of units on pH. Now you want to be careful because when we were using Gibbs free energy, we had equations there where we were using Ln or natural log, and that's where you're taking the number E and you're raising it to some power. That's not what this is. This is log log, where we're taking 10 and raising it to some power. Okay, well, why do we do that? Why don't we just talk about the concentration of hydrogen ions? Well, the main reason is because concentration of hydrogen ions is a very, very small number, and we want something so that we're not constantly having to write out times 10 to the minus 14th or whatever. So as an example, if I have a hydrogen ion concentration that's equivalent to 1 times 10 to the minus 3, and I take the negative log of that, that is going to give me a pH of 3, which is just this number up here, okay? Now, that's only going to be the case if this is also a 1. If this is something other than a 1, then this number is not so pretty. It does have a decimal involved with it, okay? But that's the reason why we use that definition, so that we don't have to write out concentrations like this all the time. And for somebody who's not super science minded, they can say, oh, pH of 4, I get that's an acid. pH of 12, I get that's a base. They understand the basic properties of an acid and base without having to get into concentrations that are a little bit more difficult for people to grasp. So that's why we use the pH scale. Okay, so make sure that you've identified on your calculator, you've used Ln or natural log before, so make sure you use the log button. Similar to pH, we can also have a pOH, which is the concentration, the negative log of the concentration of hydroxide ions in solution. And you find it exactly the same way. So if you have 1 times 10 to the minus 3 molar hydroxide ions, then the pOH is going to be 3. And pH and pOH are related to each other because if you add them together, they will give you a total of 14. All right? And that hopefully that seems logical, because when you realize that the pH scale runs up to 14, then that's what this is going to give you. Now, a little side note, it is possible to have a negative pH. It is possible to have a pH higher than 14, depending on just how great your concentration of either hydrogen or hydroxide ions is. We don't deal with that a lot, but it is possible. And I think one of the questions in your homework assignment deals with that too. So I just wanted to kind of throw that in there. The other equation that I have up here is called the ionization of water, water ionization constant. And so if you take the hydronium ions, that concentration times the concentration of the hydroxide ions, you're going to get 1 times 10 to the minus 14th. And for significant figure purposes, both this one and that figure, both of those are exact, and so they will have an infinite number of significant figures whenever you're dealing with that. The significant figures for this type of log are the same rules for the significant figures that we did for the natural log before. So if you remember those rules, the same rules are going to apply here. So let's work a couple of problems. So hopefully all this starts to make sense. If you look at example, and I will point out that I think there's an easier way to work a couple of these problems than the way that he did it, just so that you don't have to deal with all the exponents. And when we get to that, I'll show you what that looks like. Okay, so if you look at example 7.2, it says, what is the pH of a solution that has a hydronium concentration of 0.14 molar? So if I have a hydronium ion concentration of 0.14 molar, I should probably have a 0 in front of that. What is the pH of that going to be? Okay, so the biggest thing here is just to make sure that you know how to use your calculator appropriately and that you're going to end up getting the right answers. So we know that the pH is the negative log of the concentration of the hydronium ions. So therefore, the pH for this is going to be the negative log of 0.14. Now, when you type this into your calculator, you need to type in 0.14 and then hit log and then hit the negative button, okay? Because just the log of that's going to give you a negative number to begin with, and then you're going to change it so that you end up with a positive number. So when you do that, you should end up with a pH of 0.85. Okay, significant figures says that there are two numbers after the decimal point, so my final answer will also have two numbers after the decimal point. Okay, if we then look at the next problem, it says, what's the concentration of hydronium ions in a solution whose pH is 6.5? So if my pH is 6.5, and again, I know that 6.5 equals the negative log of the concentration of hydronium ions, how do you get that into your calculator? I'm not worried so much about writing it out as he did in the book as I am that you can type it into your calculator correctly. So the first thing you're going to do is, since making this negative was the last thing that you did before, that's the first thing that you're going to do now. So you're going to take that negative sign and you're going to bring it over here. So you're going to take 6.5, type that into your calculator, then hit the negative and make it a negative number. Then you're going to hit, it depends how your calculator is set up. It's either going to be second log or inverse log, depending on what kind of buttons are on your calculator. And so when you do that, you should end up with a hydronium ion concentration of 3 times 10 to the minus 7th. Now, why is there only one significant figure? Because there's only one digit after the decimal point here. So that means that I'm only going to have one significant figure in my answer. I don't count this one when I'm counting significant figures. Okay? So that's concentration of hydronium ions. That's taking it and flipping it backwards, going the other way with it. All right? So now we can actually take one of these figures and we can find pH, POH, hydronium ion concentration, hydroxide ion concentration. We can find all four of those. If we know one, we can find the other three because we know the relationships between all of them. So let's look at example 7.3, and we'll give ourselves some more space up here. Okay, so example 7.3 says, aqueous solutions of ammonia are common household cleaners. A reasonably concentrated solution of household ammonia has a pH of 11.90. So pH equals 11.90. And it wants to know the POH as well as the concentrations of hydronium and hydroxide ions. So The easiest thing to find from this, from pH, is to actually find POH, because you know that the pH plus the POH is 14. So if pH plus POH equals 14, and remember that's an exact number, then I have 11.90 plus the POH equals 14. And so, again, simple subtraction problem, and that's going to give me that I'm going to have a POH of 2.10. Okay? From there, then we can find concentration of hydronium and hydroxide. Now, what I would do is I would say, all right, if I know that the pH is 11.9, I would take 11.90, and the negative log of the concentration of the hydronium ions is going to give me the pH. So therefore, I type in 11.0, make it negative, hit inverse log, and then that's going to give me the concentration of the hydrogen ions. So I would find this directly from the pH. Make sure, again, that you are trying these problems and that you're getting the right numbers on your calculator, because that's the biggest hurdle to these types of problems, honestly, is making sure that you know how to drive your calculator and to get the right answers. Okay, so the correct answer for hydronium ions here is going to be 1.3 times 10 to the minus 12 molar. Why two significant figures? Because there are two significant figures after the decimal point here. So when we're dealing with logs, remember it's the numbers after the decimal point that matter. So 2 here means that I have 2 here. Now, in the book, when he is showing you how to find hydroxide ion concentration, what he does is he actually uses the kW and goes from this using 1 times 10 to the minus 14th and the water ionization constant to find the hydroxide ion concentration. That is a perfectly reasonable way to do it. Personally, I think it's easier to say, well, instead, I'm going to take the POH that I just calculated, the 2.10 equals the negative log of the hydroxide ions, and I'm going to find the hydroxide ion concentration that way, just because I think it's easier. For one thing, it's fewer numbers you have to type in, so it's you're reducing the chance that you're going to make any kind of an error. So again, you're going to type in 2.10, you're going to make it negative, and then you're going to take the inverse log of that. And so once you do that, you should end up with 7.7 times 10 to the minus 3 equals the hydroxide ion concentration, and that would be molar. Now let's look at this and make sure that our answers make sense. We know that it's a household cleaner. We know that cleaners are normally basic, and they gave us the pH, and so the pH looks like it should be basic. So the POH has to add up to 14, so that makes sense. If it is a basic solution, my hydroxide ion concentration should be greater than my hydrogen ion concentration. And if I look at these numbers, you can see that this number is a lot bigger than this number, because this is to the minus 3rd and this is to the minus 12th. Okay, so when I look at that, my numbers all make sense according to what I know about pH. All right, so now you're going to get some practice calculating pH and POH.